Hello, I'm Hanan Bouhmoud, PhD candidate at University Hassan II of Casablanca in Morocco and PhD Fulbrighter at Auburn University in the US. As part of the 12th International Conference Construction in the 21st Century, held in Amman, Jordan, we, Professor Dalila Ludi, Professor Salman Azhar, and I are presenting our contribution named Evaluation of Buildings Life Cycle Carbon Emissions based on Building Information Modeling and Life Cycle Assessment, and as a case study we took an affordable housing in Morocco. To start with, the climate change is a worldwide concern. For record, almost 1,700 billion tons of CO2 equivalent is the global amount of emitted greenhouse gases until 2020, 53% of which occurred in the three last decades only. To face this alarming situation, several inter-countries agreements were signed, namely the Paris Agreement, where most countries committed to reducing their greenhouse gases emissions by 2030. Each country committed to diminish its carbon emissions by conditional and unconditional percentages, called nationally determined contribution. This is in order to keep the global temperature rise to no more than 1.5 degrees Celsius. Otherwise, the world will experience extreme environmental conditions, namely drought, desertation, floods, and extinction of most flora and fauna species. For this purpose, it's necessary that all industries upgrade their current practices toward more innovative and eco-friendly technologies, namely the construction industry, which is considered as one of the most polluting industries. It's responsible for almost 33% of the global greenhouse gases emissions. Also, it's known that globally it consumes 40% of energy, generates 50% of solid waste, and uses 40% of raw materials and 15% of water. Building information modeling is a game-changing technology that proves significant potential for enhancing building infrastructure ecological performances. Some of the featured abilities are: first, optimization. It allows performing many assessment and simulation works of a facility or any construction project at an early stage without having to construct it physically. Second, decision making. It helps validating building solutions at the design stage, such as choosing between recycling on-site or off-site. Standards and code implementation. It allows integrating sustainability-related codes and rules into models at the design stage. Fourth, real-time tracking. It enables real-time tracking and detection of carbon emission problems at the operational stage. In general, it enables early assessment of embedded operational and demolition carbon emissions, adapts the building accordingly, and facilitates decision-making. Morocco is an African developing country that committed to ecological strategies in the early 21st century. In 2009, the country announced its commitment to convert 52% of the consumed electrical energy to renewable-based energy. Likewise, in 2015, it updated its nationally determined contribution to carbon emission reduction and committed to a minimum of 17% by 2030 compared to the status quo, and a maximum of 42% if foreign financial aid is obtained. In this vein, 47 important strategic projects were launched, namely building 5 of the biggest solar power plants in the world. Noor Warzazat, with a capacity of 560 megawatts of solar power, Noor Middle, with a capacity of 1600 megawatt solar power, and 3 other ongoing platforms, Noor Tata, Noor Bujdur, and Noor Layoun. The second action was preparing the legal framework, such as laws regulating the energy production, use, and direct injection to low voltage in the city's electrical network. For building sector, building energy efficiency code and thermal construction regulations in Morocco were turned mandatory in 2016. Third action was training and preparing useful tools. For that purpose, the government created specific bodies, including clusters, to ensure free training and guidance to the AEC industry operators, mainly
architectural and engineering firms to use the mandated codes and related software, such as Binaya software. However, the construction industry is still using traditional practices instead of innovative and sustainable technologies.
Therefore, the objective of our study were first, highlight the capability of building information modeling to fasten and facilitate calculating carbon emissions and help reducing buildings' impact on climate change. Second, provide a reference of carbon emission and footprint of the most common types of affordable housing adopted in Morocco. Third, reveal the top impactful building materials in terms of embedded carbon emission, disclose the most contributing component to operational carbon emission, assess and reveal the contribution share of each building stage to building life cycle carbon emissions and the related carbon footprint. For that purpose, we adopted a mixed method design where we investigated the local context, conducted a literature review, and defined the project we will consider as a case study. Then we developed the related building information models, extract quantities of the used material, and calculate EC, OC, DC, and every stage carbon footprint. And finally, analyze the results, discuss them, and conclude. The case study considered a parcel of affordable housing built on a field of 61,300 meters square in Casablanca, Morocco. It contains 65 repetitive five-story buildings with 43 building type A and 22 building type B. Building type A is a fully residential building with a built covered area of 1,232 meters square. Building B is a mixed-use building where the first floor or the ground floor is designed as a commercial area and the upper floor as a residential one. For the construction stage, the embedded carbon emission was supposed equal to the sum of emitted carbon by the used materials. So the carbon emissions related to this stage of each building type was evaluated based on the collected materials densities and carbon factors from the literature and the extracted materials quantities from building information models. Likewise, for the operational stage, the operational carbon emission was supposed the sum of emitted carbon by the consumed energy, both fossil and electrical, the used water, and the generated domestic wastes. The real quantities consumed or generated per month were collected from the field for each building type. Then, based on the fact that the operational stage is assumed to last 50 years, the all operational carbon were calculated. As a result, the fully residential buildings emit around 28 tons of CO2 equivalent, slightly more than the quantity of carbon emitted by the mixed-use buildings. In the meanwhile, the distribution of carbon emission for both types is almost the same, with the small differences. Generally, the operational stage generates almost 98% of the all building life cycle carbon emissions. The study revealed that the emitted carbon in the construction stage is mostly generated by concrete, steel, bricks, paint, and ceramic tiles. However, their weight differs according to the building types. For the fully residential buildings, it represents 90% of the embedded carbon emissions, whereas for the mixed-use building, their emissions weight is evaluated to 85%. Meantime, glass is also an impactful material for this building type, as it represents 8% of the total emission of embedded carbon. Likewise, the study highlighted that fossil energy is the most contributing to the operational carbon emissions. It's responsible for almost 3/4 of the total emissions in the operational stage, followed by the domestic waste with almost 13 to 14% of the operational carbon. On the other hand, the carbon footprint of affordable housing is around 280 CO2 equivalent per meter square for the construction stage, 21,200 for the operational stage, and only 28 CO2 equivalent per meter square for the demolition stage. The comparison revealed that the carbon footprint of the mixed-use affordable housing is 5.2% more than the carbon footprint of fully residential buildings, which is completely the opposite for both the operational stage and building life cycle carbon emission, where the carbon footprint of the fully residential affordable housing is almost 15% higher than the footprint of the mixed-use building. To sum up, the study revealed that the energy consumption is responsible for 75% of the building life cycle carbon emission, which goes along with the Moroccan climate change policy that is mostly focused on the energy efficiency. Moreover, it's revealed that concrete, steel, bricks, paint, and ceramic tiles are the most contributing materials to the embedded carbon, and that the domestic waste are the second responsible element for the operation carbon. Therefore, adopting a material and domestic waste management strategy would significantly help reducing the emitted carbon in Morocco. Also, the study confirmed that the large ecological potential of BIM technology, hence adopting BIM as a working practice could significantly help in meeting Morocco's climate change goals, which could be more achievable if the country adopts an efficient strategy toward a mandatory BIM implementation. Furthermore, the study emphasized the absence of local database of carbon factors for materials and transportation, and also the lack of statistics related to construction and demolition wastes and transportation traffic. So, developing the missing databases and statistics could be the topic of further studies and would enable both designers to select less impactful materials on the environment and contractors to use more eco-friendly construction processes, especially in terms of waste management and transportation. On the other hand, the study presents some limitation, namely the fact that it omitted the generated carbon by the built infrastructure within the project field and related facilities, such as roads, power and storage networks, landscaping, plantation, earthwork. And it used carbon factors of similar materials and transportation statistics developed in other countries. And thank you.